Hello everyone, welcome to another Wave-to-Wave webinar as part of our series on automated fiber switching technology and applications. Please have a look at our complete webinar lineup to get the full overview of beneficial impacts of automated fiber switching in various deployment applications. Looking at telcos, staying competitive and guarding long-term profitability are two crucial drivers for telcos. To assure their profitability, telcos must optimize their networks, processes, and procedures and carefully control both capital and operational expenses, commonly referred to as CapEx and OpEx. Many carriers within the telecom and cable markets are seeking new network architectures that make use of technologies and products based on data center architectures in order to achieve lower costs and service enablement flexibility. In satisfying this need, the industry has developed the central office re-architect as a data center or CORD reference architecture. CORD re-architects the CO into a data center or DC model to introduce cloud-style economies of scale and agility. Today, we will look at introducing automated fiber switching or AFS as a CORD ecosystem component. Today's webinar will showcase ways telcos can achieve the benefits of CORD's promises when seamlessly integrated with AFS products. Next slide, please. We'll start with an overview of the CORD reference architecture, focusing on key components and architectural design philosophies. This is followed by a detailed investigation into equipment deployment scenarios. Although deployment processes and procedures may vary by telco, there are some core processes and methods every telco must execute well. Once we have reviewed deployment scenarios, we will discuss the benefits of integrating AFS technology into CORD infrastructures and the immediate positive business case impacts on CapEx and OpEx expenditures. We'll conclude with a quick look at the long-term benefits of utilizing AFS technology within the telco fiber plant and network ecosystem. We show that AFS systems allow telcos to minimize time to revenue and labor requirements while simultaneously facilitating service turn-up, test, and maintenance. So let's get started. Next slide, please. The goal of CORD is not only to replace legacy network elements with more agile counterparts, but to also enable the CO to quickly support more attractive and meaningful services. Therefore, CORD has a foundation in CO equipment aggregation and disaggregation. Re-architecting equipment bundles to support software definition enable the virtually instantaneous reformulation of infrastructure needs based on new service requirements. That way, the use case applications define the network service. To support this evolution, CORD has a wide array of use cases, including R-CORD or residential CORD, which defines the architecture for residential broadband. M-CORD or mobile CORD, which defines the architecture of the radio access network, and evolved packet core of LTE 5G networks. E-CORD or enterprise CORD, which defines the architecture of enterprise services such as Ethernet business services. C-CORD or cable MSO CORD, which is a wave-to-wave suggested architecture to define triple play services capable residential architectures. A-CORD for analytics that addresses all four use cases and provide a common analytical framework for a variety of network management and marketing purposes. Based on subscriber and network deployment volume, R-CORD is considered the largest opportunity for both OpEx and CapEx reductions. Next slide, please. If you look at the typical CO over the years, it may have 300 different types of closed proprietary equipment. What that means is today's CO can be an impediment to innovation and deployment of new services. And that is what the service providers are wanting to change. Telcos are seeking new architectures that make use of technologies and product strategies to achieve lower costs and services flexibility. However, we must also be realistic and acknowledge the fact COs are not going away anytime soon. They are strategically located in the center of nearly every city and are critical assets for all types of current and future communication services. With the simplification that AFS brings to CORD architectures, deployments, and ongoing operations, the integrated AFS CORD approach can achieve a 75% reduction in OpEx. Maximum AFS benefits are realized when seamlessly integrated into the full array of CORD use cases for residential, mobile, and enterprise deployment scenarios. CORD combines software-defined networking, network function virtualization, and cloud technologies with commodity infrastructure and open building blocks to bring data center economies of scale and cloud-like flexibility to telcos. Next slide, please. The goal of CORD is not only to replace today's purpose-built hardware devices with more agile software-based counterparts, but also to make the CO an integral part of every telco's larger strategy and to enable them to support more attractive and meaningful networking services. This business strategy applies to many service provider types, including telcos, mobile network operators, and wholesale and retail carrier enterprise service providers. The first step is to virtualize existing hardware devices as illustrated by the small letter V. Virtualization transforms each device into its software counterpart and run it on commodity hardware. In the process, functionality is disaggregated and repackaged in new ways. While virtualization is an important step, we will also demonstrate maximum AFS benefits are realized when seamlessly integrated into the full array of core deployments for residential, mobile, and enterprise deployment scenarios. In order to tackle the residential use case, CORD re-architects the CO as a data center by unifying 4 related but distinct architectural threads. Next slide, please. The first is SDN, which is about separating the network's control and data planes. This makes the management and control plane open and programmable, which can lead to increased innovation. It also allows for simplification of optical access networking devices that can be built using merchant silicon, resulting in less expensive hardware. The second is NFV, which is about moving the data plane from hardware appliances to virtual machines. This reduces CapEx costs through server consolidation and replacing high-margin devices with commodity hardware. It also reduces OpEx costs through software-based orchestration. The third is cloud technologies and architectures, which defines the state-of-the-art in building scalable services, leveraging software-based solutions, microservice architectures, virtualized commodity platforms, elastic scaling, and service composition to enable network operators to rapidly innovate. Realistically, the move to an agile staging ground with virtual network functions is far too expensive to roll out if it required entirely new equipment. Telcos need to be able to utilize some of their existing CO equipment, extending their facilities as they can afford to, while deploying new classes of services as readily as possible. So the last thread is an evergreen product approach to satisfy current needs by positioning the network to be ready for tomorrow. Next slide, please. The physical infrastructure-based access network use cases, or last mile, is a challenging business. It has thousands of miles of facilities or cabling that originates from COs and cable hubs and terminate in nearly every home and building in a given serving area. It has specialized outside plant electronics deployed in cabinets, underground vaults, and mounted to utility poles. The last mile have real operational challenges, including lightning strikes, floods, backhoe fades, and even squirrels. The R-Cord architecture spans the telco CO, physical access network, and the home enterprise equipment. R-Cord includes virtualization of legacy NEs common to today's access passive optical network, namely the optical line terminal, or OLT, customer premise equipment, or CPE, and broadband network gateway, or BNG. The R-Cord strategy is to refactor key NEs as software running on commodity servers. In R-Cord, there are 2 sides of input-output, or I/O, commonly referred to as east-west traffic flows. One, shown on the right, which is west, is the metro transport referred to as I/O Metro, connecting each CO to the regional inter-office transport network. On the left side of the figure is the access network referred to as I/O access. Next slide, please. The important difference with traditional data centers is the CORD architecture does not focus on optimizing statistical multiplexing of traffic over WAN interfaces. On the other hand, CORD implementations manage massive amounts of east-west traffic and physical fiber connections. Management of these connections, along with virtual machine instantiation optimization, is easily realized when integrated with a software-definable AFS. The R-Cord switching fabric is organized as a leaf spine topology and optimized for traffic flowing east to west, since there is no north-south traffic as with the conventional data center. Traffic enters, leaves a VNF running on a virtual machine and flows east-west. Next slide, please. Our cord focuses on GPON technology and virtualizing the OLT to produce virtual OLT. There are also virtualized counterparts to the CPE and BNG. The first challenge was to create a commodity I/O blade. Telcos have developed an open specification for a GPON MAC 1RU pizza box. This board includes an essential GPON media access control or MAC chip. This replaces an existing closed and proprietary complete OLT chassis. The end result is to bring the access network interface under the same SDN-based control paradigm as the white box-based switching fabric. In other words, virtual OLT is implemented as a combination of merchant silicon or commodity GPON interface boards and an SDN control function that sets up and manages control plane functions of an OLT. Next slide, please. A legacy OLT-NE is a chassis that has power supplies, fans, and a backplane. The backplane is the interconnect technology to send bits from one card or blade to another. The legacy OLT typically includes two management blades for 1+1 redundancy, two or more uplink blades or the Metro I/O interfaces, and the rest of the slots filled up with line cards or the PON access I/O interfaces. In GPONs, the line cards have multiple GPON access ports. Within the R-cord framework, OLT disaggregation maps the legacy physical OLT-NE to the R-cord architecture. The backplane is replaced by a leaf spine switch fabric that interconnects the disaggregated OLT I/O blades. The management functions move to a separate management plane. The new Metro I/O and Access I/O blades become an integral part of the R-cord architecture as they become I/O shelves of the R-cord platform. The Access I/O blade is also referred to as the GPON OLT MAC. While VOLT, VCPE, and VBNG refer to the virtualized counterpart of the three physical devices, they are not complete or pluggable elements in R-cord until they are packaged as services. Each includes a multi-tenant service controller, and each scales independently across a set of service instantiations. The new architecture is ideal in unbundling functionality when coupled with AFS technology. Next slide, please. An automated fiber switch product such as Wave2Wave's Roam line of products offers dynamic fiber cross-connect capability at layer 1. The slide shows the AFS system located in a CO and serving multiple PONs. After the telco deploys the network and signs the first subscriber, it provisions an OLT I/O blade in the CO on one of the fibers connected to the AFS. The CO Provisioning Center remotely connects the new customer's distribution fiber to the appropriate splitter via the AFS automatically and remotely. A second subscriber signing up from any of the homes connected to the AFS system can be provisioned on the same OLT I/O blade. Therefore, the carrier can fully populate each OLT I/O blade before investing in an additional I/O blade and fibers. Telcos can also use AFS products to enable zero-touch provisioning, in which they provision new subscribers without sending a technician into the field. Zero-touch provisioning have already been implemented successfully for data centers. Zero-touch provisioning provide substantial cost savings in high-density scenarios such as multi-dwelling units or MDUs, where entry rights are often difficult to obtain from landlords. Next slide, please. Although cord deployment reduces CO equipment costs versus traditional OLT-NEs by disaggregating expensive OLTs into NFV OLT I/O blades, the good news, it dramatically increases the number of fiber ports and patch panels in the CO to manage, which is the bad news. If we look closely at the traditional versus NFV, we see that statistical multiplexing gain of traditional onboard layer 2 or network processors is not present in disaggregated I/O blades. Therefore, telcos would have a lot more fiber connections to manage during turnup and provisioning as shown in the slide. Technicians will spend a great deal of time identifying the correct fiber, conducting pre-provisioning tests, and running patch cords, all of which drive up OpEx. An integrated AFS minimizes these OpEx and headcount expenses within the R-cord CO while simultaneously maintaining proper records. Next slide, please. Another example of the need for AFS integration is facilitation of dynamic stand-up instantiation of virtual network functions such as GPON MAC IOs, application layer functions, firewalls, caching, etc. AFS supports efficient topology reconfiguration for fiber interconnects amongst VNFs. The AFS, for example, the Wave-to-Wave Roam 500 product, enables the flexibility in provisioning to support the required reliability requirements regardless of sub-cloud cluster equipment design. VNF pooled equipment coupled with automatic fiber switching products makes processing equipment more effectively shared, reducing capital and operational expenditures. For example, by increasing the size of VNF cloud clusters, it becomes difficult to switch data from an arbitrary access fiber to any VNF or OLT MAC. When the size of the VNF cluster cloud reaches a certain level, the resource sharing gain may become flat or marginal. Therefore, it's not economical to design a high-speed, non-blocking mesh VNF cluster cloud, which bodes well for an AFS to provide fiber cross-connecting. Next slide, please. New technologies, new regulations, and new competitors make everyday network decisions more complex. Adding to these challenges are the historical access network realities. No amount of our core deployments will solve backhaul fades or squirrel damage of outside plant fiber cables. Only an AFS providing protection switching and centralized remote outside plant cable testing can address the needs of telcos managing real-world R-core networks. OpEx savings can result from testing multiple fiber facilities with the same OTDR using an AFS to select the fiber to be tested. This approach enables a single OTDR to handle testing for an entire central office. New fibers being installed can be connected to an OTDR or light source in the CO. A technician arriving at the manhole or street cabinet where the fibers are to be terminated then instructs the NOC to connect the visible light source to a given target fiber, enabling the field tech to immediately identify the fiber. With an AFS, the Network Operations Center can remotely test facilities from the NOC, enabling them to troubleshoot before sending any technicians into the field. Expensive OTDR test equipment can be centrally located, readily available, and shared over multiple OLT IO MAC blades. When an outage does occur, AFS can be used to perform remote troubleshooting by connecting the affected fiber remotely to an OTDR to quickly locate the fault. Technicians can then be efficiently dispatched directly to the location of the problem fiber. Next slide, please. As we have demonstrated, replacing hardware devices with software running in VMs is a necessary first step in our core implementations, but is not sufficient to satisfy telco network services and ongoing operations requirements. All the devices in a hardware-based CO must be connected in a meaningful way that also supports telco operations and software reconfigurability. This process is often called service orchestration, and if telcos are to enjoy the same agility as cloud providers, the network element abstractions that underlie the orchestration must fully embrace the elastic scale-out of the resulting virtualized functionality, as well as the effective composition of the resulting disaggregated or unbundled functionality. A model that simply chains VMs together as though it is operating on their hardware-based counterparts will not achieve either goal. As we can see in this figure, interconnection flexibility can only be achieved by utilizing and seamlessly integrating AFS technology as a key ecosystem component within the telco network. Next slide, please. Our cord is intended to run on a collection of servers and white box switches coupled with a disaggregated packaging of media access control technologies such as GPON. These hardware elements, when coupled with an AFS, are organized into a rackable unit referred to as an access rack, which is one layer of compartmentalization up from pod server racks of a traditional data center. We recommend the configuration for a reference R-cord access rack consists of 4 hardware components. 1. Servers supporting VM instantiations. 2. Switches, both leaf and spine switches. 3. I/O blades, OLT pizza box GPON MAC interfaces and GE uplinks. 4. AFS, supporting fiber management and fiber network configurations. Next slide, please. As we have seen, AFS technology can offer powerful operational benefits when integrated with our core deployments. These benefits include faster time to revenue, dynamically scaled core appliance connectivity, end-to-end network balancing, full flexibility and automation during moves, add changes, remote testing and troubleshooting of outside plant, network optimization via near real-time fiber reconfigurations, and minimize downtime and fewer outages. Finally, AFS systems will enable our core deployments to minimize labor, eliminate mismatches resulting from human error, optimize CapEx, and facilitate testing and maintenance. Telcos can gain the OpEx savings benefits of AFS immediately while simultaneously pre-positioning the network for future R-core evolution. Last slide, please. Thank you for joining us today, and we look forward to seeing you on another webinar in the series. And please feel free to send any questions you may have to info@wave2wave.com. Have a great day and see you soon.